Hi, in this video we are going to study convergence of an integral. We have an improper integral, and we'll cover not just one way, but two ways of figuring out whether this integral converges or not. So the first way I wanted to share with you corresponds to finding the integral explicitly. So we want to find we want to find the integral from e to infinity of 1 over x ln of x explicitly. And that's something we can do because of the function we're integrating. We have a function that is actually in terms of ln of x and its derivative, 1 over x. So we can use substitution to compute the integral very easily. Now, the other way I wanted to share with you is different. The other way will concern relating the integral to a series, a sum of infinitely many terms that doesn't converge. We will see that will imply the divergence of this integral. So we will compare the integral with a sum or a series. So it's an infinite sum of numbers. I haven't been able to think of another way, but there could be many ways of proving that this integral is going to diverge. No matter which way you take, you should end up with divergence, as we will see. If you have any ideas, then I will be happy to hear from you. Please make a comment or contact me, and I'll be interested in learning about it. Okay, so let's go and try the first way, so computing the integral explicitly. So as I was saying, since we have ln of x and its derivative as part of the integrand, we can use substitution. Take u equals ln of x to compute the integral explicitly. When we make u equal to ln of x, du becomes 1 over x dx. And then the integral is going to be the limit as r goes to infinity of the integral from e to r of 1 over x ln of x dx. That's going to be the limit as r goes to infinity of the integral from 1 to ln of r of 1 over u du. Because when x equals e, u equals ln of e, and that's 1. And when x equals r, u equals ln of r. So we rewrite the integral in terms of u, and that becomes the integral from 1 to ln of r of 1 over x dx, that's du, and 1 over ln is 1 over u. And we're taking the limit as r goes to infinity. And as you can see, the integral we have in terms of u is much simpler, because now we can use the fact that the antiderivative of 1 over u is the ln of the absolute value of u, to get that the definite integral will be ln of the ln of r minus ln of 1. We evaluate the antiderivative at the limits, and the ln of 1 is 0, and the ln of 1 is 0. The ln of r, as r goes to infinity, will go to infinity, and then as ln of r goes to infinity, the ln of r will go to infinity. So this limit will be infinity. This way we have proved that the integral, the proper integral, we are given the integral from e to infinity of 1 over x ln of x dx is infinity. Okay, so this is one way. Let's try the second way. So let's go and try a comparison approach. Now often when we want to check for convergence or divergence of improper integrals, we can't compute the integral explicitly. If we're lucky, we can use substitution, we can use integration by parts or other methods, but in general, we could have an integral of a function that is not that simple. So comparison methods turn out to be much more applicable. And here I will show you one of the many ways of using comparison tests to check, to prove divergence of integrals. You can also use tests to prove convergence. So let's see. Now, since we know that the integral is divergent, that's something that we showed before, or let's say suppose we suspect that the integral is divergent, we want to find a lower bound for this integral. So we want to find that the integral of from e to infinity of 1 over x ln of x dx is greater than something that is infinity. Now, it is possible to find a bound as we realize that this function, the function we're integrating, is decreasing. And then the integral from e to infinity of the function will have to be greater than the sum of the areas of certain rectangles, and the rectangles will be chosen so that the series we end up on the right, the sum we get on the right hand side of this inequality, will diverge to infinity. And the rectangles will be chosen so that they will look like this. When we add the areas, we find something strictly less than the integral. So the integral will be the area under the curve, given that this function is positive for x greater than 8. So we have this situation. Now I'm going to choose the rectangles in a wise way. So I'm going to say, okay, let's take the rectangle that has, so here we will take the width from e to e squared, and then from e squared to e cubed, and so on. So the distance will start growing larger and larger. And let's take the height corresponding to the value of the function f at the right end. Say f of e squared for the first rectangle, f of e cubed for the second rectangle, and so on, where f is the function 1 over x ln of x. Now why do we choose e squared, e cubed for x? I choose that particular value for x because the ln of powers of e gives us the powers. So ln of n and e will cancel out, and that will give us something nice. And as we will see, it will turn out that we'll get some nice simplification, and that will make the series on the right side, very easy to deal with. So the sum of the areas of rectangles will be, so the area of the first rectangle will be the width. That would be e squared times minus e times the height. That's f of e squared. And then plus e cubed minus e squared, that's the width of the second rectangle. Then f of e cubed. And then we would add more things. We'll just keep adding areas of rectangles this way. Let me just make this a bit. Okay, and as we keep doing that, we actually find a summation. So we're going to go from n equals for instance 2 to infinity, if you like, of e to the n minus e to the n minus 1 times f of e to the n. So when n equals 2, we get the area of the first rectangle, e squared minus e times e f of e squared. When n equals 3, we get the area of the second rectangle, and so on. And this will be e to the n minus e to the n minus 1. F of e to the n is 1 over e to the n times the ln of e to the n. And here we can see that ln and e cancel out nicely. And we can divide this subtraction by e to the n to get e to the n over e to the n minus e to the n minus 1 over e to the n, that's 1 over e, or e to the minus 1, same thing. So, so here we have that the integral we were given is greater than the summation from n equals 2 to infinity of a constant times 1 over n. So I'm going to erase this part to write what we found. The summation from 2 to infinity, 1 minus 1 over e times n. 1 over n. And the constant 1 minus 1 over e can be pulled out to get 1 minus 1 over e, summation from 2 to infinity of 1 over n. And this is a tail of the harmonic series. We're doing 1/2 plus 1/3 plus 1/4, etc. And this is a tail of 1 plus 1/2 plus 1/3 plus 1/4. It's just this series, and then you subtract 1. This series is infinity, because that's the harmonic series. And in case you don't remember what the harmonic series is or how to prove that the harmonic series diverges, I suggest you take a look at another video. You just look for the harmonic series video and you will find it. But the fact is that the harmonic series diverges, and we have a tail of the harmonic series. We just have the harmonic series take away 1. But when you take away 1 from infinity, you still get infinity. So this tells us that the integral we were given is greater than infinity. But of course, if something is greater than something that diverges, then we must have divergence. So that's how that's another way we can prove that the integral diverges. Okay, that's it for this video. And if you have any questions, just make a comment, contact me, and I will be happy to help. Bye bye.